All right, here we go. Moment of truth. I'm going to do a generic example to kind of build my case. I'll do a linear example, and then I'll get to the quadratic example. All right, so our goal is to use an infinite sum to find the area under the curve and then show that it directly relates to the antiderivative like we do. So let's do this example. Let's find the area under f of x equals, let's just do x, and let's keep it from 0 to 4. All right. So the idea is as follows. I kept it linear. I'm going to make each one of these 1, 2, 3, 4. 1, 2, 3, 4. Okay, so here's the line. Close enough. And I want to find that area. Here's what we're going to do. We are going to use a Riemann sum with eventually infinitely many, infinitely skinny rectangles. That's what we're really doing. We're going to use infinitely skinny, infinitely many rectangles that will give us, added all together, the area under the curve. So let's generalize though. Let's start with just four rectangles. And let's see if we can generalize an idea. I think this is the way to go about it. So here's the first one. Here's the second. Oops. Here's the second one. Here's the third one. And the last one. Oops, this one should have been here. Oh well, you get the idea. It's not imperative that it be exact. Okay. So just like a Riemann sum, it's base times height, right? Base times height, base times height. We need to think about the base and height a different way in order to do this, adding more rectangles. So let's just take a look at this first one, for example. This guy right here. We have the base, which is 1. There's another way I want you to think about it. Another way to find the base length is if you do the end value minus the start value. So b minus a divided by the number of subintervals. Typically they call this n. So in this case, we'll call it n. So the base is equal to b minus a over n. And in this specific example I'm doing, it's 4 minus 0 over the number of subintervals, which is 4, which is 1. So yeah, it checks out. That really is 1. So the base of each of these is 1, but in general, keeping it general, we can use this right here. Okay, so remember that. This guy right here is known as the base. Sometimes we call it delta x or h or epsilon or something, but we'll call it delta x, and I'll just keep calling it base. I think it's the easiest way to think of it that way. Okay, the next part. I need a way to talk about each of these points, but keeping it general. So a way to think about x equals 1, you could do this, right? This is the hardest part right here. To talk about x equals 1, I could say that that point is a, where you started the interval, plus one of your base lengths. Because if the base length is 1, adding that will get you to the end of the rectangle's base. So b minus a over n. Think about it. If a is 0 and this base length is 1, then yeah, at 1, actually that's one way to get to this point right here. How can I talk about something like x equals 2, for example? Well, here's where the magic starts to come in. I could do the same thing. A plus the base length again, but then add it again. You see what I'm doing? It's 0, a, plus 1 base length plus another base length. So in other words, I could talk about it as a plus 2 times the base length. Okay, so what about to get to x equals 3? Same idea. A plus 3 times the base length. Well, how about to get to some random one that I'm going to call I, which is an arbitrary rectangle I'm talking about? It would just be A plus I times B minus A over N. So for example, to get to the third one, x equals 3, you'd put a 3 there. To get to the fourth one, you'd plug in a 4 there, okay? That's the end of my subinterval, but hopefully you understand what's going on here. To get to the second one, you'd plug in 2. So really, I can talk about this coordinate using this equation. I can talk about x equals 2 using this equation and just plugging in 2 for I. I can find this coordinate, the x value, by that. But I don't really care about the x value. What I care about is the y value, the height of the rectangle, this guy right here. But that's as simple as plugging in the x value, plugging in this x value into the function I'm given, into f of x, because that's how you get the y value. So lo and behold, that last kind of piece before we get to move along, to get the height of one of these rectangles is equal to your function with the appropriate x plugged in. Okay, now n is determined on the number of subintervals you have, and I, it's kind of like a summation, as we're going to see. It starts from 0, and you need to go all the way up to n. So basically, you need to get from I to n. So here's where I'm going to turn it all into kind of the summation idea. This first rectangle would be your base length, right? So the area of rectangle 1, can you see that? Is the base length, which we already said is b minus a over, and we'll keep it general for a moment, b minus a over n, times the height, which is, I'll move this down in a sec, f of a plus 1 of these b minus a over n's. To get the area of 2. So think about what that just did. That's saying the base right here times the height, the function value when I plug in this x coordinate, x equals 1, into the function. So now the area of 2 of this one, the area of 2 is equal to, again, the base of the area 2, call this area 2, which is again b minus a over n, times what I get when I plug in this to the function, 2 times b minus a over n. Because that's where I got this piece right here. The area of 3 is equal to, again, b minus a, so I'm calling this 3, over n, times f of, again, a plus, but let's get to the third. And essentially, that gets you to x equals 3. It's our a value, 0, plus 3 base lengths gets you here, and you plug that x value in to get f, the y, or the height of that rectangle. And then you need one more, so the area of 4. Area of 4 is equal to one more, b minus a over n times f of a plus 3 times b minus, nope, not 3, 4. Okay, so can we generalize this whole result? Well, you know what you're supposed to do to find the area. You would just sum all of these together. And we can do that using a sigma notation or summation. So we can say the sum from I equals 1. Now, in this case, I used 4, so we stop after 4. But if I wanted to use more, I could very easily change that 4 to something else. Of b minus a over n times f of a plus I times, that's the thing that's going to continue to iterate as you plug in different values, b minus a over n. That's the formula, almost, for finding the area under the curve using an infinite sum. Now, the thing that changes is this 4. Think about it. The more subintervals, the better. This is how you would do it with 4 subintervals, and then you could plug everything in. How would I do it with 5? Literally just change the 4 to a 5, and everything is already going to follow suit. So here's how we can do it to get the perfect value. Ready? For now, this is how we're going to do it. We're going to change this to n, the number of subintervals we want, and we're going to say n approaches infinity. That's the formula for the area under a curve using sigma or summation. Okay, so how does that work in a problem like this? I'm going to redo this example, but I'm going to do it the real way with infinite subintervals, okay? Then I'll do it with a quadratic, and then I'll be done. And you're going to see how we use those proofs in a minute. So example, again, I'm going to use f of x equals x from 0 to 4, and I'm going to use infinite subintervals. Well, as n approaches infinity. So I'm going to use the formula, okay? The formula says the following. Limit as n approaches infinity, I equals 1 to n. b minus a, so 4 minus 0, so 4, over n, times. I have to plug all of this into the function here. Well, luckily it's just going to, there's no squaring or anything. And you'll see in the next example, I actually have to square it. But you're going to plug it in. So a is 0, I is I, b is 4, a is 0 over n. And I have to simplify this. So limit as n approaches infinity, summation n I equals 1. Looks like I end up with a 16i over n squared. Now you're going to have to trust me on this one. This summation only deals with I. That's the thing that's changing up to the value of n. N does not affect anything being in the sum. I can just multiply it after I'm done. So this is a little trick. It's kind of like when we're dealing with limits and we have a variable that doesn't affect the limit, I can take it out. We haven't done a lot of that yet. We will second semester. But it's an idea where if this summation is dealing entirely with I, anything that doesn't have an I can be taken out front. So I can do this instead. I can take the 16 over n squared, and I can leave the I in. Now here comes the, then I equals 1 to n. Here comes the magic moment. We've seen this before. This was that lemma I showed you. We proved what this equaled using that identity. This is the same as n times n plus 1 over 2. We already proved that. So now I can just rewrite it like this, as 16 over n squared times n plus 1 over 2. Multiply it all together, you get a 16n squared, 16n squared over, or plus 16n. Whoa, my backdrop just went away. Weird. All over 2n, it's back, 2n squared. Otherwise known as, I can take the limit, same powers, top and bottom. That means divide the coefficients. Answer's 8. Done. Is that right? Well, we can check it. 0 to 4 of x dx, which is 1/2 x squared, from 4 to 0. Plug in 4, you get 16 divided by 2 is 8. Okay, so there's a lot going on there. I did a problem by finding the area under the curve using summations. It was built around this idea of a generalized formula using summations to find the area under anything using infinitely many, infinitely skinny rectangles. And that was the cool thing about this formula I created. I have a base that says, okay, take your endpoint minus your start point, divide by infinite subintervals. and then plug a really kind of cool, tricky base manipulation to get our x's into the function to get the heights. And then it's just base times height infinitely many times. But because we had this cool identity that I made you prove, we were able to invoke that right here. And then from that point, it was just a little bit of algebra. All right, were you able to follow it? If not, well, then now you understand why I don't cover that type of thing in AB. If you were, now you understand why I don't cover that type of stuff in AB. But let's do one more example just so you can see. And then you can put these two together to do your own. So let's see. Find the area under f of x equals x squared. And this time we'll go over 0 to 3. Okay, so same idea. It all really just comes back to using that formula, that really bizarre summation formula that we kind of had to build up. So again, you would say the limit as n approaches infinity, summation, I equals 1 to n, that doesn't change. This b minus a, the only thing that changes about it is where you are working. So this time we're going from 0 to 3, so 3 over n. By the way, by me keeping this 0, I'm keeping this very nice. As soon as that's not 0, these problems get much more annoying. And then now you've got to plug in this to the function. So 0 plus 3i over n into my function, which is x squared. So in this case, we're going to end up with a squared. So 3i over n squared in this case. Okay. Now we've got a little bit of work to do. We're going to have to multiply it out. I equals 1 to n. We have a 9. Looks like we have a 27i squared up top over an n squared on the bottom, n cubed on the bottom, sorry. Because we squared it here and then 1 here. Remember what I said in the last problem? Anything that doesn't have an I in it as a coefficient can be moved in front. It doesn't affect anything. If you kept it in there, it wouldn't really change anything. But just like integrals, we can move non-important variables that are not dependent on the index of the sum. We can move them out. And where are we at here? It's the second thing that we needed. This we have proved before. We know that this is n times 2n plus 1 times n plus 1 over 6. And then we have this 27 over n cubed. Limit as n approaches infinity. We gotta solve it all out and we're done. Notice that the n power on the top and the bottom is the same. That pretty much happens every time. So it looks like we have 27 times 2. We have a 54. 54 n cubed up top, plus a bunch of other stuff that I don't really care about, all over a 6n cubed on the bottom. And just to make sure it looks good, I hope I have this formula right. I think I do. 27 was correct. So 54 divided by 6 looks like it is 9. Let's check our answer. Area under the curve, 0 to 3, x squared dx is 1/3 x cubed from 0 to 3. Plug in 3, you get 27 over 3, which is 9, minus 0, which is 9. So now you see why we needed those formulas, because you have to be able to replace them with non-summation equivalents. And if you tried to do I cubed, you'd have to look up that one, which is way worse. And any bigger power, you'd have to look up special tricks to get things from out of summations into explicit formulas like this. This is more of a well, it's a summation, whereas this is explicit. So that's why we don't spend a lot of time with this in AB. It is not worth the trouble, but now you know. It mostly relates to this formula. If you can somehow remember this formula, the questions on the AP test are all built around this. It's this base length, keeping it general, times the starting point plus the base length iterated for however many subintervals you're doing. In this case, it's up to infinity. And then you plug that into the function. All right, so I give you one to try on your own. Good luck.